No. I'm beginning to record. So I'm trying to record the classes. That's what I was doing. Okay. Okay. So set is a collection of objects. Okay. Like what is? How is it different from a list? List also has a bunch of objects, right? How is it different from a list? It's unordered. Okay. Set. It's a collection of objects, but there's no inherent order. Okay, there is no first element or there's no second element or something like that. Okay, when you say a collection of so when you write we can write a set like this, for example. Right? So it's numbers from 1 through 6, or maybe faces of a dice. Okay, the numbers on the faces of a dice. Okay, and we write something like this. Okay, we write it between these curly brackets, and that makes it a set. Okay, there's no inherent ordering. When you ask me, you can ask me, does the number 1 belong to this set? I'll tell you yes or no. But if you ask me, is 1 the first element of the set? There's no answer to that. Okay, this is the same set as something like this. There's no difference. There is no notion of ordering between the elements. Okay, and another thing somebody mentioned is also correct. You do not repeat elements in a set. Okay, so you cannot have a set with 2 copies of one. Okay, you can't have the same object twice. Okay? There are extensions to multi-sets, but we are not worrying about this. Okay, so it's also going to be very important for us to write statements in the set comprehension way. Okay, it's not write it in terms of code. Okay, but the set comprehension or list comprehension in Python, the notation is borrowed from math, and that's actually the most common way we describe sets. Okay? You could write out numbers like this, but as you can imagine, like when you look at larger sets, this sort of approach to specifying the set goes out of hand. You have to specify too many numbers. Okay, so you want a better way to describe it. Okay, so let us say, let's also say, for example, like I want to write in omega. Okay, so we are omega is a set, and I'm thinking of omega as the set of all faces of a 6-sided dice. Okay, what are all the prime numbers here? What are all the prime numbers in omega? 1 is not a prime number. 2, 3, and 5. Okay, so I can write a set of all prime numbers as 2, 3, and 5. Okay, and in a small set like this, it makes no difference, right? But what we'll prefer and what we need to get comfortable, and you'll see many examples like this, and you'll slowly get comfortable with this. Okay, we are also going to write it like this. So we are going to say it's the set of all numbers in omega. Okay, and this colon is such that, okay, and this. Right? And so this is like the set comprehension notation. Okay, so in Python you would write it as n in omega if so you would write something like n for n in omega if n is prime. And obviously Python doesn't recognize prime, but so you have to write some statement that evaluates to that. Okay, so does this make sense? So this notation means take all elements of this set which satisfies this logical statement. Okay, so every element in omega on which this logical statement evaluates to true. Okay, same way, if I want to write even numbers, okay, even numbers of omega, how do I write it? Okay, so tell me, how would I write it? No. Let's try to do it with set comprehension bit. Right? No, 246 is fine, but the adult way. N in omega, so this sign means N. So this sign is, so everyone is everyone familiar with this symbol? Right? So this is not epsilon, this is belongs to. Okay? So N in omega, okay, such that, right, N is even. Or like just for variety, I'll write 2 divides N. Okay? Okay? N in omega such that 2 divides N. Okay? And it's exactly the same as saying N in omega such that N is even. Okay? Maybe you can come up with alternate descriptions too. Okay? So is everyone okay with this? And we'll see a lot of examples of this. Pay attention to this and we'll get used to this notation. Right? This is also a set of prime numbers. This is also the set of even numbers. Okay. So sets don't need to be, they don't need to just contain numbers, they can contain anything. Okay? There's no reason for a set to contain all objects of the same type. There could be numbers and letters, things of anything. Okay? And you can write arbitrary statements. You can write more and more complicated statements to describe sets. Okay? And you can even describe sets in a way that makes it very difficult for you to even imagine what those sets. Okay? You could also have a set of sets. Okay, that is also possible. Okay, for example, I could have something like this. I could have 1, 2, 1, 2. Okay, so I can make a set with these as the objects. Okay, I can also have a set with no elements. Okay, and we'll write it either like this, that in curly braces, like we just leave nothing in between. Okay. It's also common to see 5 for the empty set, but in this class we'll just keep it simple. We'll always use this. We'll always use like empty set, literally nothing in it. Okay. Now I could have a set of sets. Okay. You can make it like as complicated as you want. Okay. Now it turns out that this, what do you think is this set of sets? Can you give me a good description for this collection of sets? I mean, you can, so there is no one way to describe a set. Okay. As long as, so we could, for example, describe, in terms of notation, we are very clear what this set is. But in terms of notation, this has the same meaning as this. Okay? So I could specify a set completely by just writing out this. Okay? It's a collection of 4 sets, and those sets are these 4. Okay? But is there a different way you could describe this collection of sets? Maybe such that n is less than 2. But that won't have this because this is an empty set. Right? But very good. Like if we didn't have this, like a collection of all subsets of omega, where every element of the subset is less than strictly less than 3. would describe these three sets. Okay, not this one, but yeah. So, but that's good. That's a good one. Okay, but also like what I was thinking of, and this is also the collection of all subsets of one two. Okay, everyone knows what a subset is. So, so you can have this notion of subsets. Okay, and we write A is a subset of B. Okay, every element of A also belongs to B. Okay, so this set, the set containing 1 as an element, is a subset of 1, 2. It's a subset of the set containing 1, 2. Okay, so for example, 1 is a subset of 1, 2. Okay, because sometimes you'll find people make a distinction between like proper inclusion proper inclusion and inclusion with equality. They would sometimes put like a line underneath it. Okay, we won't worry about that. We'll just use the same symbol for both of us. Like a subset, A is a subset of B. If every element of A is also an element of B. Okay. Okay, so the empty set by default is a subset of all sets. Okay, the empty set does not contain any element. Okay, so so this sentence, if an element belongs to A, that's also in B. Okay, it's vacuously true. Okay, so we always think by convention, we always keep the empty set as a subset of all sets. Okay? So if you look at all possible subsets of this set containing the elements 1 and 2, the 4 of them, you can just take 1, you can just take 2, you can take both of them, or you can take neither. Okay? Those are the 4 sets that you see here. So this is a collection of subsets of the set 1, 2. Okay? So everyone okay with all of this? Yeah. 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 So there's a difference between this belongs to and this subset. Okay. So keep in mind here we said n belongs to. Okay. So n is an object. It need not be a set. Okay. N is some object that belongs to the set omega. Okay. We write n. When we write n here. Okay, when we write n in omega. Okay. N is an object that belongs to omega. It's a component of the set omega. Okay. When we write the set 1 is a subset of 1, 2. The set 1 is not an element of this set. Okay? What it means is that every element of this set is also an element of this set. There's a small difference between these two. Okay? Don't get confused between the belongs to and the subset. Keep track of the types. Okay? Right? And how many of you have seen Venn diagrams? You've all seen Venn diagrams. It's a very convenient way to think about sets. Okay, and we'll do a little bit about all of this. So generally speaking, when we draw, generally speaking, like we denote like geometric shapes. I mean, we use some geometric shapes to qualitatively say, okay, these are all the elements of the set. Okay? The idea is that the interior of the set somehow contains all the elements of the set. So it's just a visualization. Okay? So if you wanted to draw like a circle for A and a circle for B in terms of a Venn diagram, how would you draw them? Okay, you have, forget omega for now, okay? But just A, the set A We just think of it, we just draw some geometric shape, okay? And this geometric shape for us contains all the elements of this set, okay? But if I have to draw B in relation to this, okay? Remember A was all prime numbers, 2, 3, 5, and B was the set of all even numbers, 2, 4, 6. So if I have to draw the set B in relation to set A, how do I do this? So where do I draw this set A? Any of you want to draw this? Autocorrect issue. Right? So you do draw, thank you. You draw B with an overlap. Okay, so this sort of qualitative relations are very important. So when we draw the Venn diagrams, the shapes are just arbitrary, okay, but the qualitative relations, they're kind of important, okay. The idea is that there is an overlap between these two sets. The element 2 belongs to both of them. There are some elements that exclusively belong to one of these sets, okay, and so this is the story. And when we draw this picture, we don't really put the elements here. We don't really write the elements of the sets. It's just like a convenient visualization. Okay. Now, so these are two sets. When you draw, so you can, what's the union of these two sets? What's the union of A and B? 2, 3, 4, 5, 6. These are sets that belong to either A or B. Okay? And a lot of people have taken discrete math, the non-logical statements. Okay? What symbol did we use for OR? This symbol for OR. B. Yeah. You would have used B for OR. Okay, and it's not an accident that we use something that looks like a B for union. Okay, when you are dealing with sets, okay, when you are working with sets, the union is completely equivalent of the logical OR. Okay, so and that's why we look at the set comprehension statements. Remember, like for A, we had this, we associated the set A with this logical statement, n is prime. Okay, the set B we associated with 2 divide sign. Okay, the logical OR of these two statements, these two logical statements, when we do the logical OR of these two, okay, that's the description of the union. Okay, so they're completely equivalent, and that's the reason the symbol for union looks like the symbol for OR. Okay, so n is prime or 2 divides. We do even better than that. With sets, there is something we do even more convenient than that. But yeah, you could use any Boolean statement for the descriptions of the set, any Boolean operation on the descriptions of the sets, and you would be doing the corresponding set operation. Okay? So there's actually no difference between, they're conceptually identical, and that's the reason we choose this U for union and the inverted U for intersection that we'll see in a little bit. Okay? So, right, so and yeah, so what is A intersection B? So is everyone familiar with this notation? Everyone definitely knows the logical OR, right? Right? So because I know most of you have taken this with that, but maybe not all. Okay? So does everyone know what a logical OR is? Everybody? Okay. Right? So the symbol we'll use is this V. Okay? That's the common symbol we use for OR. but I'll, in the initial few classes, I'll also write or on top just so you remember. Okay. What is the intersection of these two sets? It's the element 2, right? What logical operation will it correspond to? The logical AND. Okay, so this is the collection of all elements of omega that evaluate to true on this statement, right? And the wedge symbol is wedge symbol, remember V. The wedge symbol is the symbol for a logical AND. Okay. So intersection of sets is like the actually this to the logical AND of the corresponding logical equivalent of this. Okay. So these are intersections and unions. Now, they don't need to be with sets with a finite number of elements. We are just doing it just to draw pictures easily. Okay. So normally speaking, we also have like a reference set, a universe. Okay. That's kind of like the set of all possibilities. Right? Here we are talking about the faces of a dice. And we set up all faces of a dice, there is 1, 2, 3, 4, 5, 6. Okay. So typically in Venn diagrams, and I think somebody actually asked, somebody just mentioned this before when I was drawing. Whoever did this absolutely right. We usually have the notion of a universe, okay, that sort of captures all the possibilities we are interested in for a particular problem. Okay. So these two are subsets of the universe. A and B are subsets of the universe. We are generally going to be dealing with subsets of the universe. Okay. There may be elements that do not belong to any of these sets that we are thinking. For example, the number 1. Okay. Now, but also associated with it. But once we fix a reference, okay, once we fix a reference universe, okay, we have another kind of statement. So there is a logical and logical OR. Okay. What is a unary logical operator? That elementary unary logical operator. So there's and or. What's the other basic thing that we think about? No. Yeah. So and we have an equivalent of that too. Okay. So we would write a complement with a little c on top. Okay. So a complement is the set of all elements that do not belong to A but are in the universe. Okay. So when you write a complement, it's always with respect to some universe. Okay. So that's why when I was just writing unions and intersections, I didn't think of a universe. I didn't tell you anything about the universe. And I have to tell you about complements. I need to think about what's the reference universe. Okay. So a complement is the set of all elements in A that are so all elements that are not in A but are there in the universe. Okay. And what is a complement? And right? And so this is the set of all n in omega. I'm going to write this for naught. Okay. Okay, what is B complement you can write in a similar way. Okay, and what is A union B complement? Just one. How do you write it in terms of A complement and B complement? Right. So A union B is the set of all elements, just A union B Okay, this A union B. These are all elements that are there in either A or B. If they belong to at least one set, they are in this A union B. Okay. If I want to find an element that is not in A union B, it must be true for that element that it's not there in A, and it must not be there in B. Okay. So this will be A complement intersection B complement. This applies to any number of sets like A union B union C complement, is A complement and B complement and C complement. A complement intersection B complement intersection C complement. Okay. And what is A intersection B complement? Right. So A intersection B are elements that belong to both A and B. Okay. So if an element should not be in A intersection B, all you need for that element is that it's not there in either of the other. Okay. So what is A intersection B complement? Very good. A complement, union, B complement. Okay, for something to be not there in the intersection of A and B, okay, either one of this should be true. It's either not in A or not in B. Okay, that makes it A complement, union, B complement. Okay, and again, like A intersection B intersection C complement is A complement, union, B complement, union, C complement. Okay, does that make sense? Okay, very good. So these are like the very basic elementary operations on sets that you kind of already know. We're just also making a connection with logical statements, and that's like an exercise. Write the set comprehension notation for both of these. Okay, A union B complement and A intersection B complement. Okay, fill up the set comprehension notation for both of these. Okay, if you have any trouble with it, just ask me. I'll help you with it. Okay. You think in terms of logical statements and just write out the logical statements. That's all you need to do. Okay. Now there is something which is very crucial for us. Like some of you have seen permutations and combinations and varieties, but it's useful to put them in like one framework. Okay, and for that, like there is the notion of a Cartesian product. Okay, that's a product between sets. This is called the Cartesian product. Okay, you can take any two sets. Okay, you can take any two sets and you can define something called the Cartesian product between these two sets. Okay, the order is important. A times B is not the same as B times A. Okay, the order is important. Okay, now A times B, the way we define the Cartesian product is as follows. A times B does not lie in this Venn diagram. Okay, the elements of the Cartesian product of A and B, they're not elements of omega, they're not elements of A or elements of B. Okay, instead, these are a set of ordered pairs, okay, or sequences of length or vectors of length. Okay, the first element of the sequence of length 2 comes from A. The second element of the sequence of length 2 comes from B. So that's why the order is important. Okay, so it's a set of all lists of length 2. First element of the list comes from A. Second element of the list comes from B. Does that make sense? Okay. So tell me what is the Cartesian product of A and B? Enumerate it. so remember A is 2, 3, 5. A contains elements 2, 3, and 5. B contains elements 2, 4, and 6. Partition product of A and B is. Start with one element. Give me a sequence of length 2 or a list of length 2, where the first element of the list comes from A, the second element comes from B. Yeah, is that? 2, 4, okay. So for these lists, we will use parentheses, the regular parentheses like this. I don't know if I'm calling them right, but these regular parentheses, these are lists. This is not a set. This 2, 4 is a sequence of length 2. The ordering is important. 2, 4 is not equal to 2. Okay, so this is one element, for example. Okay, but we want to enumerate all the elements of the partition product. How do you do that? Do it systematically, so we don't miss anything. So hold on to one element of A. Hold on to one element of A. So I'm going to write the element of A in blue and follow it up with each of the elements of B. Okay. Okay. Then I write the next element of A, pair it with each element of B. And the next element of A, which is 5, pair it with each element. Okay, this is called the Cartesian product of A and B. Okay, so here, what's the, we also have to note the size of the set. Okay, so the size of the finite set, like A or B, is the number of elements that are there in the set. Okay, so A has size 2 and B has size 3. Okay, it's also called the cardinality of the set. So that it's also not uncommon to just refer it to the size, refer it as the size of this. So the size of cardinality of the set is the number of elements in the set. Okay. Here A has 3 elements, B has 3 elements. What's the cardinality of A times B, the Cartesian product of A and B? Times 3. And that's the reason we have this notation. If A had size 10 and B had size 2, what would be the size of the Cartesian product of A and B? A has size, let's say A has size 10 and B has size 2. What would be the size of the Cartesian product of A and B? 20, 10 times 2. Okay, that's because you would write, if I wrote it like this, you would write 10 rows, okay, 10 rows of elements like this if you write it systematically, and each row would have 2 elements. Okay, so totally 10 times 2. And that's also the reason to write this, this notation. The size of the Cartesian product of A and B is the product of the sizes of A and B. Okay. So everyone okay with this? Okay. There is one last thing that we think about is the set that we already saw, the set of all subsets of a set. Okay, the set of all subsets of a set, it's called the power set. Okay, so if I take this set, all subsets, okay, we saw this before. Okay, all the subsets of this, these are all the subsets of 1, 2. Okay. This is called the power set of a set. and it's usually denoted by 2 to the set. Okay. Also, because if any set has k elements, the size of its power set is 2 to the k. Okay. And why is that, we will see next class when we have to do some of these problems. Okay. But the set of all subsets of a set is called the power set, and it's called the power set because it has size equal to the exponent of the size of the set. Okay. So 1, 2 has 2 elements. So the power set of 2 has 2 to the 2, that is 4 elements. There are 4 subsets of 1, 2. Okay. And here we have seen it. This example we have exhaustively written everything out. Let's see why it's doing here. Okay. So this is the power set. Okay, so these are some of the very elementary things that we have with sets. You might have seen many of these, but there may also be some of the things that you haven't seen before, at least not in this form. You may have this everything of it. Okay. So these are the elementary notions that we have with sets. But there is one additional thing that we'll pay attention to. Okay, it's called the indicator function of a set. Okay. So in general, like you told me, when you define a function, okay, the function, when you define a function in Python, right, that the inputs need to be from a particular set. Okay, yeah, set of all outputs is another set. Okay, so generally speaking, that's the that comes from the regular notation for a function. We always give it a name. The name of the function here, I'm calling it f. Okay, and I always write it like this. I write a colon and I write 2 sets. Okay, I take a domain. This D is for domain, R is for range, and that's like the common names used. You don't have to remember those. Okay, but basically, when we write a notation like this, what it means is that f is the name of this function. It takes elements from D and assigns to each element in D some element in R. Okay. Every element of D is mapped to some element of R. Okay. Not all elements of R need to be exhausted. Okay. Some element in R may not be a map of any element in D, that is okay. Okay. But every element in D has exactly one map in R. Okay. So it's like D is the set of inputs. What the function does is it takes every input and it gives you one output. Okay. It's very crucial that it's only one output. Okay. That's what makes it a function. So an indicator function. So what the indicator function of a set is a special kind of function. Right, and we'll find that this is extremely useful for us when we are thinking about probability in general, but also when we are thinking about logical things we do with sets. Okay? It's a way to convert, like somebody was asking about Boolean algebra with logical equivalents of sets. We can do one better. We can actually do arithmetic operations with logical equivalents of sets. Okay? So the indicator function, when we define an indicator function, as I said, again, like we have in mind some reference set, the omega. Okay? There's some universe, and the indicator function, we usually write it as 1. Okay? This is a function. So let's say like I want to define the indicator function of a set A. Okay? So this is a function. I'm going to call this function 1, 2. Whenever I write this funny 1, it means it's some sort of an indicator function. This is a function from omega to the set 0, 1. okay, which means that this is the name of the function. Name is not important for now. Okay, it takes every element, for every element in omega, it assigns one of these two values. Okay, so it's a function where I feed it any element of the universe, it spits out either 0 or 1. Okay, it tells me 0 or 1. Okay. Does this make sense? So, no, we'll keep it as omega. Okay, so it takes any element of the universe, and to this element it assigns 0 or 1. The idea is this: the indicator function. So it tells me if the argument of the function, if I feed it an argument, it tells me if that argument of the function belongs to the set A or not. Okay, so here, like, we just recall that omega was 1, 2, 3 to 6, A was 2, 3, and 5. Okay, so the indicator function of A at 1 is, does 1 belong to the set A? No, so it returns 0. Okay, the indicator function for the element 2, what is it? 1. What's the element? Chance. Yeah. Okay, what's the indicator function for indicator of A for the element 3? 1. Yeah. Indicator of the element 4 is, you can be more confident, 0. Right? It's a pretty simple notion. It's a pretty simple notion, but it's very powerful. Okay, and so on. Right? So to each element of the universe, it assigns a 1 or a 0. Okay, and only to, it assigns a 0 to everything outside of set A. It assigns 1 to everything inside of set A. Okay, and it will have the indicator function for each. Okay. Now, yeah, so that's it. Yeah. So an indicator function, it's basically a function from the universe to 0, 1. So we are just calling them indicator functions. Right? So these are binary values. So 0, 1 value functions. Their output is always either 0 or 1. Their output cannot be 2, for example. Okay? Their output is always 0 or 1. They can, their functions on the universe, its output is always 0 or 1. Okay, any function like that is the indicator function of some subset of the universe. Okay. So that's the general idea. Okay. Now you have the indicator function for A. You can have a similar indicator function for B. And now tell me, what is the indicator function of A union? Union is complicated. A intersection B. What's the indicator function for A intersection B? Right? So if you look at the Venn diagram, right? When you look at the Venn diagram, I'm just going to copy this again. Okay, so when you look at the Venn diagram, so when you think of this indicator function, so it is 0 or everywhere here, 1 within A, and 0 everywhere outside it. Okay? Indicator function for B, similar. 0 everywhere outside B, 1 inside B. What's the indicator function of A intersection B? Pardon? What is 0 times 1? 0. What is 1 times 1? Right? So tell me, what is the product of these, the arithmetic product of this indicator functions? So one point to note, the do this notation, right? So if f is a function from some set to real numbers, okay, g is another function from some set to real, from the same set to real numbers. Okay, let's think of it as omega, omega. Okay, when we write fg, okay, or f plus g, or f plus 1, or 2 to the f or something, okay, what it means is that for every element of omega, evaluate, so take an element of omega, take an element x of omega, f of x is the value assigned by the function f to x. G of x is the value assigned by the function g to x. Okay, fg is a function that assigns value f of x times g of x to x. Okay, it's what you think it will be, but useful to clarify this. The same thing for f plus g. The same thing for 2 to the f. Same thing for 3 times 2 to the f. Okay, so evaluate for any point x, evaluate both functions at that point, and use those numbers to evaluate the composition of functions. What is the product of these indicator functions? Right, so on 1, both of those functions are 0. Okay, so it is 0. On 3, the indicator function for a is 1, but the indicator function for z is 0. Okay, so it evaluates to the product of the indicator functions evaluates to 0 on 3. The product evaluates to 0 on 5 as well. It evaluates to 0 on 4 as well. Okay, and on 6 as well. It was 4 and 6 because the indicator of A is 0. Okay, but in the intersection, both of them will be 1. That's the only time it will be 1. Okay, so the indicator function for the intersection of A and B is simple arithmetic product of the two indicator functions. Okay, let me just give you a problem. What's the indicator function for A complement? You can think about it. You can think about this. This is just 1 minus the indicator function for it. Right? And every element. So if I look at 4, the indicator function of A on 4 is 0. 1 minus 0 is 1. And so this belongs to A complement. Okay. So just think about both of these two. We will continue with more of these. And just as a challenge, try to come up with the indicator function for A union B. Okay. A union B.